Friends, very good morning to everyone. We were dealing with the reactions of photochemistry. The reactions which are induced by light energy is photochemistry. They are photochemical reactions. We have seen that based on the quantum yield, they are classified into three categories. Today's subject of discussion is those photochemical reaction whose quantum yield is less than 1. The finest example for this is dissociation of acetone. Acetone in vapor phase absorbs light energy of a wavelength of 313 nanometer and it gets excited. The excited molecule over here dissociates into acetyl group and methyl group. They are formed as radicals. The acetyl radical loses carbon monoxide and give rise to methyl radical. Ultimately, acetone loses carbon monoxide to give methyl radical. This is the dissociation of acetone. The methyl radicals which are formed are unstable. That's why two methyl radicals can combine together to give ethane, or before this acetyl group loses carbon monoxide can combine together and cause dimerization to give rise to alpha diketone, or the acetyl radical and the methyl radical which are formed methyl radical can abstract the hydrogen from the acetyl radical and gives rise to the ketene. Dimerization of anthracene to dianthracene is another example which has the quantum yield of less than 1. Two molecules of anthracene absorbs UV light and gives rise to the dimer, that is dianthracene. The quantum yield has been calculated to be 2, but actually experimentally it is found to be zero point 0.5. What is the reason behind this? The reason behind this is that the reaction is reversible. The dianthracene which is formed gets converted into anthracene in the presence of the same light energy. As it is a reversible reaction, as soon as the dimer is formed, dimer gets back converted again to anthracene, and that's why its quantum yield is reduced to 0.5. How to measure the rate of reaction in this photochemistry? We can use chemical actinometer. An actinometer measures the amount of radiations absorbed and correlates with the rate of chemical reaction. That is chemical actinometer. The widely used chemical actinometer is uranyl oxalate actinometer. Uranyl oxalate actinometer consists of 0.05 moles of oxalic acid and 0.01 mole of uranyl sulfate dissolved in water. When this mixture is exposed to radiation, oxalic acid undergoes decomposition to give rise to carbon dioxide, carbon monoxide and water. The uranium ions absorbs the light energy and it gets activated. This activated uranium ions reacts with oxalic acid, and this energy is transferred to oxalic acid, and this oxalic acid dissociated into carbon dioxide, carbon monoxide and water, and uranium ions gets reduced and comes down to the ground state. The excess oxalic acid which has not been converted, if we measure the amount of oxalic acid present, then it gives the amount of radiation absorbed by the oxalic acid. The residual concentration of oxalic acid can be found out by titrating with standard potassium permanganate solution. The amount of oxalic acid consumed in the reaction is the measure of the intensity of radiation. The calculation of the amount of radiation is observed is done like this. We take the cell which is empty or filled with the solvent and is exposed to radiation, and after that reading is noted down. This gives the total incident energy. The cell is filled with reactants and then irradiated, and again reading is noted down, and that gives the residual energy. The difference between the residual energy and the total incident energy, it gives rise to the amount of energy consumed by the reacting mixture. This in turn gives the amount of radiation observed, and by this we can calculate the rate of chemical reaction. This is how the quantum yield can be measured. In the coming presentation, we can deal with other types of photochemical reactions. Till then, have a nice day. Thank you.